Welcome to the ET380 lecture video on antenna systems number 1. Antennas are transducers which convert electrical power into electromagnetic waves. Transmitting antennas convert electrical signals into electromagnetic waves and radiates them. A receiving antenna converts those electromagnetic waves from received beam into an electrical signal. Two-wave communication is used for both transmission and reception. Radio signals are electromagnetic waves, which is a combination of electrical field and a magnetic field. The magnetic fields are produced when a current is passed through a conductor. Here's a diagram of E and H planes. And this is a horizontal antenna, and we have two planes, an E plane, which is electrical, and it's the direction of maximum radiation, and we have the H plane, or magnetic field, and these two planes are at right angles. Okay, for basic types of antennas, we have a physical structure of the antenna, the frequency range of operation, and the mode of the applications. And physical antenna structures are broken down into wire, aperture, reflector, lens, microstrip, and arrays. Other antenna classifications are the frequency of operation and the mode of operation, so point-to-point, broadcasting applications, radar communications, and satellite communications. Okay, we use frequency when we have a sine wave here, and that depends on the number of alternations within a period of time. And our period, which goes from one cycle to the other, the time low or to the time high, and that is 1 over frequency. Here I'm showing a sine wave, and this is where we're measuring wavelength. So it's also the same distance as a period, but instead of frequency, we're going to make it a distance. So our formulas are here for meters and here for feet, and that is a wave in air. Here are two basic types of antennas, Hertz and Marconi. So Hertz is a horizontal and physical half wave, and Marconis are usually vertical. They're physically 1/4 wavelength, and they're electrically 1/2 wavelength long, and a ground plane or a counterpose is needed. Here are other antenna classifications. The wire type includes dipole and monopole, which we're going to cover, and also helix and loop, which I'll cover later. Here is a diagram of a half-wave dipole antenna. Dipole means two poles, and it's also known as a Hertz antenna or doublet. So here we see the incoming transmission line, which is the line that feeds from the amplifier. Here's a conductor in two pieces. It is a 1/2 wavelength. Each half is a 1/4 wavelength, and the basic resistance is, or impedance is, 73 ohms. Half-wave dipole antennas have some advantages. The impedance is not sensitive. It matches well with transmission line impedance, especially the old 300 ohm cable. It has a reasonable length, is relatively easy to build. The disadvantage is not very effective due to a single element, but it can work better if we combine with other elements. The application of our radio receivers. This is a fairly easy ham radio antenna. It's also used for television receivers, and it's used in a wide variety of applications. Actually, here I'm showing an actual example of a half-wave dipole antenna. And I backtracked from our formula that's on our homework, and I started with a 50-foot wavelength, and then I went back and calculated, so we got a 9.36 kilohertz. And We have a 73 ohm basic resistance, and I chose a coax, an RG59U, which is a 75 ohm, and here's a standard coax picture. And you see it has two elements between insulators and some kind of a structure holding it. Here I'm showing radiation pattern for a half-wave dipole antenna. Here we have a two-dimensional diagram, and we show the radiation pattern. Our antenna goes through the center, and that's half view 2D. Here's a three-dimensional view with our antenna going through this center, so it's kind of a tire shape, and that is the radiation pattern. And you can see that we have very little transmission at 90 degrees. Okay, here I'm showing the standing wave on a dipole antenna, the red being the voltage and the blue being current, and that shows the radiation patterns. Okay, here I'm showing the radiation pattern of a receiving dipole. So E would be the magnetic wave and V would be the voltage wave. And this receiving antenna is picking up the magnetic wave and converting it to an electrical signal. Here's a folded dipole antenna, which is another dipole wire, and here we're showing a diagram, and we have a continuous loop of wire fed from our feed and the old twin lead, and we have a spacing we can measure, and it is a half wavelength. And here is a commercially available folded dipole. Here's an example of a folded dipole antenna that we can make from our twin lead, 300 ohm, and we twist the ends, we break it in the center, and we have our twin lead. So we could go ahead and build an antenna basically from this readily available antenna wire. The advantages of a folded dipole antenna is that it has higher input impedance than the standard dipole. It draws lower current from the source, matches well with the characteristic impedance of a transmission line, better bandwidth characteristics than a single dipole of the same size, offers superior signal to noise ratio performance, has good signal reception, receives a desired signal from the band frequency without losing signal quality. The disadvantages are the displacement adjustment of the antenna are very difficult, and outdoor management antenna can be difficult when antenna size increases. The folded dipole antenna is used for feeder element, a Yagi antenna, parabolic antennas, turnstile antennas, log periodic antennas, phased and reflector arrays, radio receivers, and TV receivers, and we'll cover most of those different types of antennas later. Let's cover dummy antennas. Dummy antennas are used as a load in place of a normal antenna, and they are supposed to match the impedance of the transmitter. They emit minimum radiation, they dissipate radiated power as heat, and they're used during tuning and testing of amplifiers, and their unnecessary rate of radiation is a poor procedure and illegal. So these are used when we're testing equipment without actually broadcasting. The field strength of an antenna, the actual signal level at a particular geographic location. And the standard is the amount of voltage induced in a 1 meter piece of wire. Voltage decreases with the distance from the antenna, so the distance is doubled, the voltage is halved, and the distance is halved, then the voltage is doubled. Okay, let's talk about antenna gain. There is no actual amplification occurring in an antenna. The gain is only a comparison of signals received from the reference antenna and the test antenna. The difference in signal levels received is expressed in decibels. Only two reference antenna types are accepted, isotropic and dipole. Okay, isotropic radiation. It's simulated by a lamp shining inside of a sphere, and the lamp's at the center, and it illuminates the interior equally at all points. So there's equal power radiated in every direction on the lamp. So the gain is expressed in dBi when the reference to an isotropic, and gain is expressed in dBd when the reference is a dipole. So a dipole radiates mostly at right angles and is very little off the ends. So here is a picture of a sphere, and that's essentially why we represent isotropic radiation. Reciprocity is the function that a broadcasting antenna that's transmitting and a receiving antenna that's receiving have the same receiving pattern.